Hi guys, it's Mrs. Harmison here with your notes on energy. We are going to touch on three main types of energy in this lesson. First of all, kinetic energy is the energy that an object has because it is in motion. Gravitational potential energy is stored energy due to an object's height. And elastic potential energy is stored energy due to stretching or compressing. Here are the formulas that you're going to need. First of all, each of these types of energy are going to be measured in joules. Another thing it's going to be helpful to know is that on Mastering Physics, sometimes potential energy can be abbreviated with a U. The other things that you need to know in these equations are that M stands for mass in kilograms, and it has to be in kilograms. V stands for velocity, and it has to be in meters per second. Again, mass in kilograms here. G is going to be 9.8 meters per second squared, just like we've used acceleration due to gravity before. And then H is the height, and that height is off of the ground and measured in meters. For your elastic potential energy equation, K is something called a spring constant. And that spring constant is different for each spring. And the spring constant is measured in newtons per meter. And then X in this equation is the stretching or compression. And so that is going to be measured in meters. That's going to be how far a spring has been stretched or compressed. And now we're just going to work some practice problems similar to the ones that are on your Mastering Physics assignment. So this first one says, at what speed does a 1,400 kilogram car have the same kinetic energy as a 25,000 kilogram truck going 32 kilometers per hour? So for this car, we know its mass is 1,400 kilograms. We want to know its velocity. We need to figure out its kinetic energy, but we know that its kinetic energy is the same as the truck. So the truck has a mass of 25,000 kilograms and a velocity of 32 kilometers per hour, which we're going to have to convert. When we type all that in, we get 8.889 meters per second. To calculate the kinetic energy, we're going to use the formula. Kinetic energy equals 1/2 mv squared. So the kinetic energy is going to be 1/2 times 25,000 times 8.889 squared, which ends up being 987,657 joules. That's the kinetic energy of the truck. Since we want the kinetic energy to be the same, we're going to take that number and do this equation again, but now for the car. So we're going to take 1/2 of the mass, which is 1,400, times the velocity squared, and we leave that as v because that's what we're solving for. And when we solve that, we get a velocity of 38 meters per second. Okay, in this one it says a train is traveling at 50 meters per second. How fast would the train have to go in order to double its kinetic energy? The problem is it doesn't give us a mass. So what we can do is we can assign a mass. And I recommend always assigning the easiest thing you can think of. In this case, I would just call the mass of the train 1 kilogram. We could say we're talking about a little toy train. And its velocity is going to be 50 meters per second. And so you can calculate its kinetic energy, which is going to be 1/2 times the mass times the velocity squared. And when you do that, you get 1,250 joules. And then it wants to know the velocity if this is doubled. So if we double this kinetic energy, we get 2,500 joules. So now if we set 2,500 equal to 1/2 same mass, because we're talking about the same train, now we want to find out its velocity, and then we solve for v. We find that it needs to go like 70.7 meters per second in order to double its kinetic energy. All right, and then the second part says, by what factor does the train's kinetic energy increase if its speed doubles to 100 meters per second? So we're talking about the same train, so we're going to give it a mass of 1 kilogram again, and now it has a velocity of 100 meters per second. So we can calculate its kinetic energy, 1/2 times its mass times its velocity squared. And when we do that, we get 5,000 joules. So whenever it asks by what factor, you're going to take the bigger number, 5,000, divided by the smaller number. So in this case, kinetic energy before we doubled its speed, so 1,250, like we solved for in the last problem, and you actually come up with an even number 4. So this tells us that the train's kinetic energy increases by a factor of 4. A fielder tosses a 0.15 kilogram baseball at 28 meters per second at a 30-degree angle to the horizontal. So the baseball is going something like this. And we have 30 degrees here, and we have 28 meters per second here. All right, now right at the very beginning, it hasn't divided up into x and y yet. So its entire velocity is 28 meters per second. So if it says what is the ball's kinetic energy at the start of its motion, we're just going to use our equation. 1/2 times mass times the velocity squared. And when you do that, you come up with 58.8 joules. But the second part wants to know what is the kinetic energy at this point right here. So at the very top of its arc, it's going to go up and it's going to come down, and we want to know the kinetic energy at the top of its arc. As the ball travels, it's moving upward and it's moving horizontally, but at this point, it stops moving upward and it starts to move downward. But right at that peak, it has a velocity in the y direction of 0. So we know that the only velocity that the ball has right at this point is its x velocity. So we can use our triangle that we drew up here to figure out what the Vx is. You get an answer of 24.2 meters per second. And so since this is the only velocity the ball has at this point, we can then plug that into the equation for kinetic energy. Still the same ball, so we have the same mass, but now we only have 24.2 squared for our velocity, and we end up with 43.9 joules as our answer. Your sister, who has a mass of 45 kilograms, is sitting on a swing with 3.2 meter long chains. We can calculate the potential energy of your sister from that data. The formula for potential energy is PE equals mgh. So we can calculate her mass times g, which is 9.8, times the height, which is the length of these chains. And when we calculate that, we get 1,411 joules. So this right here is 1,411 joules. And then what's happening is you're pulling her back this way so that the chains make an angle of 32 degrees with the vertical. And so what we have is a right triangle right here. So now she's back over here. We want to figure out what this potential energy is. So we have a hypotenuse of 1,411 and an angle of 32. And we want to find this value right here. This is the adjacent, so we're going to use cosine. We get 1197. So to find the difference, we take 1411 minus 1197, and we come up with a difference of 214 joules. Okay, in this problem, it's talking about the difference between sprinters and non-athletes and their tendons, and it wants us to find out the difference in the maximum stored energy between the sprinters and the non-athletes. So we're going to look at the sprinters and we're going to look at the non-athletes. Now the sprinters, it says that they have a stretching of 43 millimeters, which 43 millimeters is going to be 0.043 meters, and then the non-athletes have a stretching of 0.033 meters. So they both have a spring constant of 33 newtons per millimeter. Now we're going to have to convert that. So 33 newtons per millimeter, we would get 33,000 newtons per meter. For both of these, K would be 33,000. You would use the formula, potential energy of a spring equals 1/2 kx squared for both of these, and then subtract them to find the difference.